Today I want to talk about our project with the collaboration of Csiro. We were working on optimization of the solar cells. Our industry supervisor was Regine, our academic supervisor Mehdi and Tafik. They helped us a lot during this journey. And Amor, Baba, myself and Michael, we were the teammates that were working at this project. During this presentation, we're going to go through all these outlines, which started from the motivation to the conclusion and summary. Firstly, initially during this process, we went through different articles, and as you know, the trend of global warming and climate change is increasing, and that's why the idea of smart homes becomes growing. Smart homes contain from smart automated devices which are user-friendly, environmental-friendly with high efficiency, and they provide comfortability in their occupants' life. Csiro provided printed solar cells. These solar cells can come up together and be as a blind. These blinds are able to provide the enough energy which is needed for the movement of them and which is needed for the motorization of them. Our final product, which is a standalone system from these solar blinds, these blinds are printed from organic ink. They are they use sustainable material to provide them. They are semi-transparent and flexible, which is the huge advantage of them in compared with other conventional blinds, which made from silicone, which is unsustainable and it's not transparent at all. But these products are semi-transparent. Moreover, we were able to provide a standalone system which doesn't need backup energy. That's why it doesn't need the wiring, and also by automation of them, the need of human interval will minimize. Moreover, as I said, these ink are organic, and unsustainable material which is used in the PV, which is silicone, is eliminated. By providing this product, smart lighting is approachable in a smart home. Moreover, we are producing energy from the window area. The window, if we put conventional PV on the window area, there is not a window anymore. It becomes as a wall. But as this prototype is semi-transparent, we can take advantage of the window and produce energy from the window area. These blinds were controlled manually in the Csiro company. We were able to motorizing them, and we were able to do the mechanical and electrical design, which is efficient and suitable for a standalone system which doesn't need the backup. Moreover, we were able to do 3D printing for the mechanical components of the system, and doing coding by the Arduino board, which is the main part of which is the brain of this prototype. Now I want to hand the presentation to Baba, and he's going to talk about the feasibility study of this project.
Thanks, Kiana. So for feasibility study, we have some calculations here. First of all, we know that this is, as Kiana has touched on, we have a standalone system. So we need to make sure that the consumption of the equipment is less than the production. So we have to calculate the instant power. So for doing so, we have the specifications of the blinds with the current and with the voltage. So the instant power is 6 watts. Let's say, for example, in a month like July, that we have got 2.7 hours of good sunshine, we can make about 2.7 multiplied by 6 watts energy. But for picking the right size of the battery, we shouldn't consider July. We should consider a month like January, which has approximately 7 hours of sunshine, in order to make sure that we can store all the energy in the battery during the day. And we also have 2 motors here, as we have 2 types of movements, one for sliding the motors and one for changing the angles of the motor. So for doing this, we needed to calculate the force needed to move the blinds. But at the start of the project, we didn't have the design of the project and we didn't know which 3D printer is going to do our work, so we didn't know the material. But alternative way was to calculate the use the fish scale to calculate the force needed to move the conventional blinds. So for doing so, it turned out for the changing of the blinds, we needed the smaller motor, which has got 14 Newton centimeters torque, and for the bigger motor, we needed 26 Newton centimeters. And as you can see, the circuit here is not good, it is not beautiful, it's quite complicated, but if you break down to smaller parts, we have got the buck boost converter here, and the Arduino board, which is the brain of the system, LDR system, LDR, two micro switches, LCD, A4988 motor drivers, two of them, and two stepper motors, and 4800 lithium battery with the capacity of 4800 milliampere hours. So I hand over the presentation to Ammar to talk about the circuits.
Thank you, Babak. We have two methodologies over here. One is the design of electrical components and the other one is mechanical design. For electrical design, we have a block diagram. So we are getting power from these solar blinds and we are converting this power to 12 volts by the help of DC-DC buck boost converter. So it's charging the battery with 12 volts and this battery is giving the power to the whole circuit, which involves the controller and the motors and an LCD as well. So solar blinds, for solar blinds we get 0.6 volts in a single strip. In a single module there are 4 strips and in a single string there are 5 modules. So in multiplying all these all together we get almost 12 to 13 volts output from the solar blinds. So it is not consistent, it is changing according to the sun. So we need a buck boost converter to convert these voltages into 12 volts. So buck boost DC converter take an input of 5 to 30 volts and provide an output of 0.5 to 35 volts with an current of 3 amperes. So we can adjust the output of the buck boost converter by the help of potentiometer installed on it. We have a battery of 4800 milliamperes capacity, and motors, we are using stepper motors NEMA 17 and NEMA 14 to do the work. The step angle is 1.8 degree and the steps per revolution for the motor is 200 revolutions. Motor drivers used to drive these motors are A4988. The main advantage of using these circuit boards is to limit the current in the whole circuit. It will limit the current while they are not operating. So it can take two outputs from the Arduino board. One is to control the number of steps and the other one is to control the direction. So the controller we are using is Arduino Uno and the language we are using is C++. So how this system will gonna work? We have an LDR installed in the prototype. So this LDR will sense the intensity of light falling upon it and it will change accordingly. So it will sense whether it is a day or it is a night. So it will command the Arduino that it is day. Arduino will give the command to the motors to operate, and these motors are controlled by the switches. When they are decompressing, the micro switches are installed on both ends. So when they hit the micro switch, they will stop the Arduino will stop the motors, and it will show the state of the charge as well. The state of charge it shows the battery percentage left in the battery. This is the complete circuit diagram of the so this is Arduino. Ultimately we are taking 4 inputs. 2 of the inputs are for switches, 1 of the input is for LDR and the other input is for voltage divider. So ultimately we are using 14 output pins from the Arduino. Now following this I will hand over the presentation to Michael to talk about the mechanical design.
Thanks, Ammar. So ultimately we've got over here one of our early prototype models, but to get there we first got the industry project proposal and we broke it down and we saw the current prototype that's available at the moment, and looked at that and understood took away the major components of that and how that operated, and we designed our own system. Now ultimately this system will be running off 2 linear bearings, one on either side, and the pulley system will rotate it according to the steps of the motor. So that'll be run off a simple ratio, and we're able to calculate how far we need to turn it. This system, however, was quite bulky and heavy, and we need to optimize it mechanically. So we moved through that. We were able to optimize the design, as you see here, and run a static load analysis on it. Now this one here is currently operating with 10 kilos of vertical force at the blinds location. However, this is much more significant than anything that the blinds will ever be able to produce. So ultimately the factor of safety is coming close to 50. So we're very happy with this. However, we still added a cross member here to ensure that any sort of accidents wouldn't critically damage the main modules. So from here we've got our final assembly just here. So we've got the modules running along the bearings, or along the linear bearings and along the shafts, and then we've got a hex bar here that the worm drive attached to it will be able to slide along. And so ultimately these modules will be able to collapse, as you'll see in one of the following slides when we talk about the results. However, the main objective was to try and use as many off-the-shelf parts as possible, but we'll go into that a little bit later. So our project plan, initially, we had to obviously initiate the plan. So we were pulling apart the proposal and things like that, and we were sort of planning out how we were going to attack the system, how certain critical elements would operate within each other. And so finally we were able to get our project plan submission at the end of week 6, as a lot of the students know, and supervisors know as well. But also following that, we were able to start executing. So we were able to start building our plan, or building our circuitry and our physical models. So we were able to have a prototype build approval at that point. So that was a critical step for us to ensure that we started manufacture of the product, and we were able to test. And so we had the 2 weeks to test following that. I'll now pass it on to Bobak to discuss these elements of the circuitry.
Thanks, Michael. So talking about the results of the project, the first picture here shows the buck boost converter with the output voltage of that. So in this picture we use the power supply to increase or decrease the voltage, and the output will remain the same, which is 12 volts. And the other picture shows the LCD with the battery percentage with the diagram of that. And the next picture is the serial monitoring of the Arduino board. So we can see the values of LDR, micro switches, and the voltage dividers here. And the last picture over there shows the current, which is 0.02. So the light is on, and you might not see it clearly, which shows the power consumption in the power saving mode, and with the voltage of 17 volts. And I will hand over the presentation to Michael to talk about more results in mechanical side.
Alright, so as I was discussing before, we had 3 different types of printers that we were going to use. Now just briefly, we went through this one, which was our PLA printer. It was quite a cheap model, and we used that to build a quick prototype. The turnaround for the parts were about 10 to 15 minutes, which made it ideal to test and make iterations and see how they work together. As we were coming towards the final model, however, the large piece that we were talking about was done in a Stratasys Object 30, which is a polyjet printer, allowing for much higher accuracy, much more reliability, and the structural integrity was significant. The analysis that you saw before utilized the values that Stratasys has put out about their cured final product. So those results are very accurate. And then finally, with all the smaller components, we're able to load them up on the tier time with multiple runs operating in a simultaneous time. This is now our blinds in operation here. So ultimately, you might have seen in the top left corner, the sun has disappeared. So this is simulating nighttime. They turn 90 degrees and then we'll slide across. And we've got some images over here of the more final model as well. I'm going to pass it over to Amar for our conclusions
Thank
now
you.
too.
Our key learning is how to design the electrical parts and how to design the mechanical parts and the collaboration between them. The main thing we learned in this project is how to work in a team. So we have achieved a highly efficient system with minimal loss of power. It's functional and standalone system. For the next stage, we need to finalize the framing system of the whole prototype. So future work, Bluetooth connectivity can be done in future, and in future buttons can be installed as well, and maximum power point tracking can be done on this one as well.
Finally, I want to thank Csiro for giving us the opportunity to work with them. Our industry supervisor, Regine Chandler, which helped us a lot during this project, and our academic supervisor, Mehdi and Kafir, Career Success Program, and Yvonne, our unit convener, and Frederick. Thank you so much, and thanks you all for coming here.